Well, we're back here in Chapter 14, Part 2, Introduction to Inference. Today, we're going to talk more about confidence intervals. Constructing confidence intervals. Now, estimation is the process of using sample data to estimate the value of a population parameter. It basically involves two steps. We have to obtain the value of a statistic that estimates the value of the parameter that we're looking for. This value, this statistic, is called a point estimate. Step 2 is to quantify the accuracy and precision of the point estimate using a confidence interval. Now, this requires a knowledge of the sampling distribution of the statistics, Chapter 11. So make sure that you understand Chapter 11. Now, confidence interval estimates consists of an interval of likely values for the population parameter that you're looking for, and it's determined from sample information. Associated with the interval is a percentage. We call that percentage the level of confidence. That measures one's confidence that the true parameter value lies within the interval. So what does this level of confidence represent? Well, let's consider a process for calculating confidence intervals with, let's say, a 90% level of confidence from a sample. Now, assume that we did know what the population mean was and the population standard deviation, and that it was normally distributed. We're going to go on and obtain a series of 50 random samples. So we're going to take simple random samples and do that 50 times of sample size whatever, let's say sample size 15. We're going to apply our process for constructing a confidence interval for each of these random samples to obtain a confidence interval for each of the samples. What we would expect is that 90% of these confidence intervals, of these 50 confidence intervals we just constructed, would contain the true population mean. So about 45 of them would contain the mean, 5 would not. So the level of confidence represents the expected proportion of these random intervals, these random confidence intervals that we made, will contain the parameter if a large number of different samples is obtained. Now, the level of confidence is always expressed as a percent. Although the choice of the level of confidence is at the discretion of the experimenter, it will always be a percent. And the most commonly used confidence intervals are the 90, 95, and 99% confidence intervals. Now, the level of confidence is associated with a number called alpha. This is called the error rate. For the error rate alpha, the level of confidence is 1 minus alpha times 100%. Let's see how this works. If I'm talking about a 90% confidence interval, my alpha is going to be 10%. I just take 1 minus alpha, that gives me my confidence level. And conversely, if I wanted to find from a confidence level what my alpha is, I would say 1 minus my confidence level to get the alpha, the error rate. So if I have an alpha of 0.05, then what is my confidence interval? Well, I say 1 minus alpha, that's 0.95, and you multiply that by 100 to give us the percentage, 95%. We could also do the same for a 99% confidence interval, and we see that the alpha for that is 0.01. So let's put everything together. We're using a point estimate, that's a statistic, to estimate a population parameter. For example, I can use the sample mean to estimate mu, the population mean. That's what we're going to be doing in this chapter. When we wish to construct a confidence interval with an error rate alpha, so the level of confidence will be 1 minus alpha times 100. That will give us the percent. To quantify the accuracy and precision of that point estimate. Now, with each specific sample we construct, this 1 minus alpha times 100% confidence interval, then we do repeated samples. We expect that those 1 minus alpha times 100% confidence intervals of these resulting intervals will contain the actual value of a population parameter. So this level of confidence, again, it refers to the confidence in our method. not our confidence that a specific interval contains the true value of the parameter. It's in building these confidence intervals, we know that if we did it over and over and over again let's say that we're doing a 95% confidence level confidence interval, that if we took random samples, 100 times, and I'm doing a 95% confidence interval, about 95 of those confidence intervals will contain the true mean. So it gives us a confidence about our method. That is, that our method works to find an interval that contains the parameter we're looking for. So we have a level C confidence interval, that 1 minus alpha times 100% confidence interval. It has two parts. It has our estimate plus or minus a margin of error. So you're going to take your estimate, your x bar, you're going to subtract a number, this margin of error, and you're going to take that very same sample mean and add a number, this thing called the margin of error. That will give us an interval of numbers that we expect or hope that the population mean would be in. Now, the confidence level C, which is the probability that the interval will capture the true parameter value in repeated samples. So it's sort of our success rate for the method. So it's time to take a look at a very simplistic example. We're going to take a sample of size 100, and we're going to calculate the sample mean. If we're given that the population standard deviation is 5, we want to compute the 90, 95, and 99% confidence intervals. And remember, in this chapter, we assume that we have simple random samples, that the sigma, that is the population standard deviation, is given to us, and that the population that our sample comes from is normal. So with that in mind, this is how we would construct the confidence interval. We're given x bar equals 15, n is 100, and sigma is 5. So to build a 90% confidence interval, our critical value is z alpha over 2, and that is 1.645. Remember, we did all the different critical values for confidence intervals earlier. So remember how a confidence interval, when we're given the particular information that we're given, it would be to take our estimate and add and subtract off of that the margin of error. So here's our x bar, plus or minus, and here is the margin of error. It's the critical value times and what is that number? Sigma over the square root of n. We call that the standard error of our sampling distribution. So our margin of error is nothing more than the critical value times the standard error. So I plug in all those numbers. X bar in this case is 15. Our critical value, we know, is 1.645. 5 was given to us as our population standard deviation, and we have a sample of 100, so our n is 100. So I put those numbers in, then I keep calculating, so I get 15 plus or minus 0.822. So I'm going to subtract that from 15, add it to 15, and I'll get the confidence interval of 14.18, comma 15.82. And that would be in parentheses. That's how we write up a confidence interval. Now the interpretation, which is very important, which would be what would go into a report, would be the mean of our variable is between 14.18 and 15.82 with a 90% confidence interval. And if you had variable values, or like if it were in meters or whatever, you put that in there too also. Now let's look at a 95% confidence interval. Oh, well, first of all, let's talk about what's the margin of error. Well, the margin of error here is just our critical value times the standard error, which we calculated as 0.822. And the interval length is just twice that. Because remember, the margin of error, another way to say that is, it's the half width of our confidence interval. So the whole interval length is 1.644. Another way you could find that is just take the range of our intervals, subtract these two numbers, you get the same thing. So we're going to look at the 95 and the 99% confidence interval. And there they are. Take a look at the calculations and make sure that you can get the same thing that I have. And when we return, we're going to come back to this example and do a couple of other things.